All right, let's give an example of a one-way chi-square. Now, as I said in the previous lesson, the previous section, I should say, there are a lot of different versions of chi-square depending on your research design. And it can get very confusing on just how to run the chi-square based on the conditions you're in. That's why I'm limiting this lesson to just 2 types of one-way chi-square lessons. And please rest assured that on the exam, you may be given an example question that is very similar to one of these 2 types. Or it'll be a 2-way chi-square, which actually is a little easier to conduct. But first, a one-way chi-square, one-way meaning there's only one independent variable. So here's our experiment. The hypothesis is about family income and spanking. And the question goes something like this: were you spanked as a child? And the hypothesis is families that were in greater poverty would involve themselves with more spanking. So poorer individuals spank their kids more. So the simple question was asked on the survey. 2 questions were asked. How much money did your family make? Maybe when you're in high school or something like that. And then, were you spanked as a child? Yes or no. So this is the dependent variable, and it's nominal, so we have to use a chi-square. So here's what we set up. We have 4 levels of the independent variable. Here's the independent variable, family income. We have 4 levels. Income less than 20K, from 20 to 40, from 40 to 60, and over 60K. And then, were you spanked as a child? Now here's the special setup of this experiment. What's important is that there are 50 subjects in each of these levels. Each of these groups, or sometimes with chi-square we call these cells. So this is a cell, this is a cell, this is a cell, this is a cell. They're also a level and a group, a level and a group. Okay? So what's special about this experiment is there's 50, 50, 50, 50. It doesn't always happen with science. People drop out, you don't get even numbers. But in this case, this example, we have 1 independent variable, we have an even number of subjects in each group, and it's a simple yes/no question. Okay? So let's go to our formula. So this is the chi-square formula. It's actually a pretty simple formula. We just really have 2 variables here. We have f sub o and f sub e. And f means frequency. So the frequency of observed and the frequency expected. So the frequency observed is the data you collected. So the f sub o for this cell would be 45. F sub o for this one is 25, and so on. So this says we're going to sum this combination, f sub o minus f sub e squared over s sub v. You're going to want one of these for every cell you have. So since we have 4 cells, we're going to want 4 of these added together. And that's the first thing I would do, is do something like this, put them out in a piece of paper and pencil, and then slowly substitute the information. Now the f sub o is the easy part because it's already given to you. So 45, 25, 26, and 24. We want to put that wherever these f sub o's are. 45, 26, whatever I said. Okay, right on down the line. The f sub o's are in there. The tricky part of chi-square is f sub e, and it's actually trickier with one-way chi-square. F sub e is the expected frequency if the null hypothesis were true. The expected frequency if the null hypothesis were true. Well, null hypothesis means that these cells are all the same, right? There's no difference between them. That's what the null hypothesis is. The question is, where this gets a little dicey, is you could put 0, 0, 0, 0, and it would satisfy the null hypothesis. You could put 50, 50, 50, 50, and it would satisfy the null hypothesis. And unfortunately, you can get some debate over which is the best to use. Here's my answer. If it is a yes/no question, you only have 2 choices, and there are 50 subjects in here. Then if half said yes and half said no, that would be the most neutral position. So I would argue that 25 is the expected frequency you would use if the null hypothesis were true. 25, 25, 25, 25. I hope you get that. Only in a situation where you have an equal number of subjects and you have this dichotomous dependent variable where there's only 2 options, you split it in half and you put 25 here. So the expected frequency for this problem is going to be 25. So wherever you see an f sub e, you're going to plug in a 25. Every single f sub e you see, you're going to plug in a 25, and there it is right there. Plug in the numbers, do the work, you end up with a chi-square of 16.08. Good for you. Now we want to see if it's significant. In order to see if it's significant, we need a degrees of freedom value, which is k minus 1. K in this case is the number of cells. We had 4 cells. 4 minus 1 is 3. We'll assume we're going to find significance at 0.05. Degrees of freedom at 3, we just calculated, means we have a critical chi-square value of 7.815. Does ours surpass that? Yes, it does. So this chi-square is significant. We can reject the null hypothesis. There is a significance on social income and spanking.